So this is CS 162 on lecture number 16. We have finished the web module. So if you really didn't like thinking about HTTP and all the exploits that come with string substitution and code, we are now done with that. We won't be thinking about that for any longer, although you will need to remember it for project 3 and for the final. So please keep them in mind. But yeah, today we're going to move into our networking module. Just going through the same announcements as yesterday and the day before. Homework 5 was released and it's going to be due on next Monday. We still have design reviews going up. So tomorrow will be the last day this week that we have design reviews. If it seems like there's still enough demand, we might do them next week as well, or maybe we'll add some last minute slots on Fridays. But if you do want to go over it with a TA or an instructor, that opportunity is still available to you. I have been fairly lonely these past couple of mornings, I think probably because it's an 8 a.m. session, but that's fine. Project 1 write-up grades were released, so you can go ahead and look at those on Gradescope. The design doc draft is due today, so please get that submitted if you haven't already. And the optional lab 1 is due around at the end of the semester. It's totally optional, but I think it's pretty fun if you have the extra time to spare. So just to recap what we talked about last week, it's a different module, but it's all right. We talked about SQL injection, which relies on SQL servers, which web servers use to store data. If you use untrusted input as SQL that's going to be parsed, then this gives the opportunity for attackers to run their own queries and exploit that hole in your system. If you don't give the attacker any feedback, this is blind SQL injection, which is annoying, but it's still pretty easy to exploit. For some defenses that we have are input sanitization, so making sure that we don't use dangerous characters or we escape them correctly. But this is difficult to implement, and the bulletproof defense that we talked about is prepared statements, which you should always use because it's pretty much available anywhere. We also generalize this idea to command injection, basically for any parsed language that is used with untrusted input. And the defense is just to keep it simple and making sure you're using safe API calls. We talked about the example of, say, running an entire shell command. Instead, you probably just want to execute the program directly rather than spawning a shell. I also talked a bit about CAPTCHAs. So the overarching problem that this solves is that we usually don't want bots to interact with our sites, only humans. So we create these challenges that are hard for bots, but easy for humans. So this might be reading text or identifying images. Nowadays, it's more of an issue of whether you're willing to spend the extra money for paying for CAPTCHA solving services, which outsource this to mass amounts of low-paid workers. And you also see that a lot of the CAPTCHAs nowadays are really just there to provide training data for machine learning algorithms. Some issues are that CAPTCHAs are getting harder and harder because computers are getting smarter and smarter, and sometimes it can be really difficult for humans to solve. Also, not all bots are bad, so sometimes we want to let in good bots like web crawlers or Evanbot, so those might be bots that we want to let in, but there's no way to create a CAPTCHA that can distinguish the intent. All right. Today, we just have two main things that we're going to talk about, and only one thing that we're really just going to dive into in great depth. So today is really setting up the foundation of what the internet really is, and it's going to be building the requisite knowledge that you will hopefully retain as we go throughout this module, because it will be fairly necessary for understanding the rest of the concepts. So first question that we can ask ourselves is, what is the internet? I think we all use this term fairly loosely, but let's just define what these things are with their real terms. So a network is really just a set of connected machines, and these machines can communicate with each other. So right now, my computer is connected to a network. This computer can communicate with my phone, which is also on the network, and it can communicate with my laptop, which is also on that same network. These machines have all agreed on a certain protocol. So these machines have a certain set of rules that they'll use to communicate with each other. It knows that, if it sends this sequence of bits, it means this. If it sends another sequence of bits, it means something else. When we talk about the internet, we're talking about the global network of computers. So my computer, it's not limited to just communicating with my phone or my laptop. It can communicate with Google. It could communicate with Berkeley servers. I guess it can communicate with Zoom servers because hopefully you can all see my screen and hear me right now. And the internet allows us to send data between pretty much any computer that you choose. Usually when people say the internet, sometimes they'll just mean, say, the World Wide Web, which we've been talking about for the web unit, but it's not just limited to your browser and web servers. It can also be something like SSH. It could be the email protocol, which is something separate, or it could be a separate protocol that maybe Zoom uses, because Zoom's probably not using web protocols. It's probably using something else. So that's what the internet is as a whole. It's just a global network of computers that can all talk to each other. When we talk about protocols, these are really just an agreement between two machines that specifies two things, syntax and semantics. So syntax just says, how is communication specified? How do we structure our messages? What frequency do we send bits at, and so on and so forth. It just dictates how you should send things. And the semantics dictate what things mean. So maybe 00 is, I don't know, disconnect, and 11 is I want to make a new connection, just as an arbitrary example. This doesn't just have to be technical as well. We could have a protocol for, say, asking questions in lecture. Step one of this hypothetical / actually real protocol is a student should raise their hand. Because it's Zoom, maybe this isn't as relevant, but you can technically raise your hand in Zoom, so we're going to go with this. Step two is going to be that the student waits to be called on by the speaker or waits for the speaker to pause. In a larger class, maybe the second part is irrelevant, but the idea is the student can't just immediately speak right away. They have to wait as part of this protocol. Otherwise, they're just being rude. Step three, the student speaks the question after being called on or after this waiting period. So after a certain amount of waiting period, then the student speaks their question. And then this isn't really a step, but there's this, I'm not sure what to call it. Basically just a way of being recognized in case you're not noticed. The protocol specifies that it's okay for you to say like, excuse me or something if you don't know, if the speaker doesn't notice you. So again, not too relevant in the Zoom setting, but this is what you would do in something like a real lecture, hopefully next fall. All right, that's the internet and protocols. Nothing too complicated yet, but are there any questions on anything? Okay, awesome. So now that we've talked about protocols, we're going to talk about how we layer these protocols together. And this is all going to go into something that we're calling the OSI model. So when we layer layers together, we say that each layer has a certain protocol. So each layer communicates things in a certain way. Each layer is going to rely on services that are provided by the layer below it. And each layer is going to provide services to the layer above it. This is analogous to when we're writing applications, how these applications are layered on top of other libraries and protocols and so on and so forth. So when we write code, that code might import a library, which will abstract certain things away from us. Maybe that library makes certain calls to the operating system itself. So if it needs to open a file or change something that only the operating system can do, it will do that. Then the operating system might handle, oh, if it's trying to open a file, I have to speak to this hard drive. And that's like something really complicated that the program is never going to have to worry about. And even lower than that, maybe when we ask to speak to specifically the hard drive, it has to send certain bits down the wire, then the hard drive has to manipulate certain things on its disk. So this is just an example of how layering is applied outside of the internet. We're going to go into another example of how two, I guess in this example, they might be CEOs of a company and they want to communicate with each other, but they don't have time to, go to each other and speak face to face because they're busy doing whatever it is that CEOs do. So of course we have Alice and Bob. And Alice wants to send a message. It's really important that right now she tells Bob that she's hungry. So Alice isn't going to just walk to Bob. Instead, she's just going to hand it off to her secretary. So her secretary gets this message and she tells her secretary, oh, could you just send this message to Bob, please? This secretary goes, okay, well, it's not the secretary's job to physically walk to the building. So now the secretary is going to pass it on to the mail system. And the mail system, now it's the mail system's job to pass this message on. So this message gets sent to whoever the mail carrier for Bob is. Bob's secretary receives this message and it sees, oh, this message should go to Bob and not like, I don't know, Carol. So the secretary goes to Bob and says, okay, here's a message it came from Alice and I didn't read what it said. I'm just going to give it to you. Now Bob opens up this message and sees, oh, Alice really wanted to tell me that she was hungry. And we think about it, each of these layers was communicating with each other in its own way. Between Alice and Bob, all Alice knows is I wanted to speak to Bob and I got a message through to Bob saying that she was hungry. The secretary's only job is just to make sure that this message gets to Bob. The secretary didn't care what the message said. The secretary just needed to make sure it got to where it needed to get to. But the secretary's job is also not to send messages to addresses, only to people. So the secretary hands it off to the postal service, and the postal service job is to send messages to specific addresses. So each of these layers is doing its own function, and it's relying on the layers below to fulfill what it needs to do its own job. And here's what I said, except just in a single sentence. So it's the same in the internet. With the OSI model, it's called the Open Systems Interconnection Model. You don't need to remember this. It's just the OSI model. And it models how internet communication works in the real world. You'll notice that it goes 1, 2, 3, 4, 7. That's because there used to be a layer 5 and a layer 6 level, which I believe was called session and presentation respectively. But these really ended up just being theoretical concepts that didn't really see any use in the real world. So we just are going to ignore them for now. You just need to remember 1, 2, 3, 4, and 7. It's going to have the same abstraction ideas that we talked about in the mail example or that we talked about in the code example. Each layer can be implemented in different ways as long as it provides the correct abstractions to the levels above it, and if it gets the correct services from the layers below it. This means that we could possibly switch different protocols in the middle of transporting a message as long as all of the abstractions are fulfilled. So going into the first layer, this is the physical layer. This one's pretty simple. What it really does is just send some bits from me to somewhere else. So my computer is sending bits from its Ethernet port or from its port in the back to some other device on this network that's handling it from there on. This could be something like, oh, send a 0 as a low voltage and a 1 as a high voltage. Or maybe if you're using something like fiber optic cables, a 1 could be a flash of light and a 0 is something dark. Or it could be something like radio frequency modulation, so RF modulation. If something like my phone wants to communicate, it's not connected through wires, it's actually sending signals as radio frequencies through the airs, and those 1s and 0s are encoded inside of those signals. So some real world examples, you're not responsible for these either, are the Wi-Fi radios, which use a protocol called IEEE 802.11, or Ethernet voltages, which are part of IEEE 802.3. This is really just a diagram of how this would work. We have two nodes here, A and B. A just wants to send this sequence of bits to B, and that's all that we really get from this protocol. This is great, but usually we want to do more than just send bits to the device that we're sitting right next to. So next, on top of this, we're going to try to talk to multiple devices, not just one. This is called the link layer. In the link layer, we're going to send an abstraction called frames directly from one device to a number of other devices. This relies upon being able to send bits, because if I can't send bits, then I can't really communicate with anything. And when we send bits, groups of bits from one device to another, we're going to package all of these bits together in a structure called a frame. So I might send a frame to someone else, and then another frame to a different device on the network. These protocols, the main one is generally the Ethernet protocol, which is also IEEE 802.1. And the idea is that it looks something like this. We have a construct known as a local area network, or LAN, and these computers can all directly address one another. So this computer A, it could talk to B, or it could talk to C, or it could talk to D, and it needs some way of being able to send bits, and B knows, oh, this message is not for me, so I'm going to ignore it, or, oh, this message is for me, so I'm going to capture this message and read it and pass it to the layer above. Generally, these are going to be consisting of multiple physical links. So oftentimes you don't see like literally a giant bar with all of the devices connected to it at the same time. But we won't worry about that too much. And I do have a blue slide next that talks briefly on that. In general, frames have to consist of 3 things. This is where I would normally ask you what these 3 things are, but unfortunately, I've given away the answer in this packet right here, or in this frame right here. So I'll just go through it. It needs to have the source. So usually we want to know where the message is coming from. It needs to have the destination. So it needs to know who the message is going to, so that other computers know to ignore this message. And it needs to have the data, because we want to include the data as part of the message that we want to send. Questions on layer 2 or layer 1, I guess? All right. Just as a quick aside, usually if you've ever plugged in a computer before, you know that you're not plugging it in directly into like a shared bar where all the computers see exactly the same thing. Usually we're connecting them as like a bunch of wires to each other, but the key is still that my computer can talk directly, in quotes, to any device on the network. So we just emulate this by whenever a device receives a message, it's just going to send it to everyone else that it sees, so that if A sends a message, it will always be received by E, no matter what happens. Just as a quick aside, in case you were confused why you were plugging your computer into like a single port and not like a bar. Like I mentioned, Ethernet is the main protocol here. So this is an example of what an Ethernet frame looks like. You can see that we have our source MAC address, which I'll get into MAC addresses in a moment. It has a destination address, and it has a couple of other generic data that you don't need to worry about too much, and then the actual data that we're trying to send. So all of this gets packaged up into a sequence of bits, and these bits get transmitted down the wire. Ethernet is the most common layer 2 protocol. I think there are a couple others, but I wouldn't be able to tell you what they were off the top of my head. And Ethernet relies on MAC addresses. So MAC addresses are a 6-byte address that identifies a piece of network equipment. So for example, my computer has a Wi-Fi card, which has one MAC address, and an Ethernet cable or an Ethernet port that has another MAC address. Usually these will be written out as 6 bytes with colons separating them in between. So we've got 1, 2, 3, 4, 5, 6 bytes here. The first 3 are assigned to manufacturers. So maybe Intel gets a bunch of, maybe not Intel, Apple gets a bunch of first 3-byte addresses, and Intel gets some 3-byte addresses, and then other companies get the same as well. And then the next 3 bytes are device specific. Very good question. These MACs are not in any way related to MACs from crypto. It's just that the letters MAC are kind of apparently common in the computer world. In crypto, MAC refers to message authentication codes. In networking, MAC refers to media access control. So very good question. They're not related in any way whatsoever, and I apologize because I know it's confusing. We'll get into this later when we talk about WPA as well. But yeah, okay, so this is a diagram of link 2, layer 2. Layer 2 just says, how do I make sure that this message, how do I send this message from A to C and make sure that no one else, accidentally receives this message and thinks it's for them. All right. On top of this, it's not really feasible for us to directly address every single computer on the internet. So we need to build something on top of this that allows us to address every single device that exists in the entire internet. So this is layer 3. It's called the network layer. It's really the internetwork layer, but we call it the network layer for reasons that I'm not entirely sure of. But this provides sending packets from any device on the internet to literally any other device on the internet. This is going to rely on what we built earlier, where we can send frames directly from one computer in our network to another computer in our network. And when we want to send messages, we're going to put them into groups of bits, and we call these packets. So whereas layer 2 works in terms of frames for its bits, layer 3 works in terms of packets. When we want to talk between one network and another, we need to bridge them together somehow, and we'll talk about how we get into addressing. The internet protocol is really the only protocol that exists at this level, and it's the one that we're going to talk about. I believe it's next lecture. So when we have two networks like this, all of these computers can directly address every other device. But again, this doesn't scale to the size of the internet. My computer can't directly talk to a computer halfway around the Earth while still maintaining some sense of efficiency in its internal network structures. Just ignore that last sentence I said. I'm not sure where I was going there. But this would not scale. This model would not scale well. So instead, we're going to say that we can send packets indirectly by routing it across different devices. Each hop is allowed to use its own physical and link layers, as long as eventually my packet goes from the source all the way to the destination, taking as many hops as it wants in between. So this is what one of these might look like. I have A and I have D, and I want to send this message all the way across the internet. So A says, oh, I can't directly address D because it's halfway around the world and I can't efficiently do that. So instead, I'm going to forward it to this network here. This network knows I also don't have direct access to D, but I'll send it on closer to the destination, send it to this middle node here. This will forward it on to this node here. And this router knows, oh, I can actually forward this directly to D, so I'm going to forward it here, and D receives the message. So again, this is a different abstraction before, because in the previous model, layer 2, A can just directly send a message to D, but that's inefficient. So now we've built a system where we can forward messages from one place to another. And the other useful thing is that each link here can be a different protocol. So maybe A is communicating with its router through Wi-Fi, like my phone is, and these routers are communicating with each other through Ethernet or some other wired protocol because it's fast. The key is that this packet is always going to use the internet protocol no matter what the layers below are providing, because the layers below are just providing direct communication, and internet protocol can be built on any of these possible layer 2s while maintaining the same layer 3. Questions on this so far? All right. So for packets, we basically need the same three things as before. We need to know where's the message coming from. We need to know where's the message going, so the destination. And again, we want to know what does the message actually say. Again, similar to frames because we're trying to achieve similar things, except this time it's indirect. We're also going to say that packets can be fragmented into smaller packets. Because the different links can be different, we need to support any possible maximum packet sizes. Thus, if a layer or if a router receives a packet and it knows, oh, I need to forward this on, but this link that I want to forward it to, it doesn't support packets that are this large. It's going to fragment that packet, send smaller packets, and then when the recipient receives it, it has to reassemble them in order to form the original packet. So this is just something that we have to build in because IP supports so many different kinds of links. The job of the router is really just to route the packets to the next hop. So it forwards them closer to the destination would be the ideal scenario. We'll cover how a router knows how to forward packets as well as how we attack the system next lecture. So that's coming very soon if you're really curious about that. We also don't guarantee anything about the route that a packet takes. If I send 2 packets to the same destination, one might take one route, one might take the other route. And the only thing is that eventually the packets will hopefully get to the correct location. On something like the internet, why might 2 packets take different routes? Let's say I send a packet and it goes down a certain route. Why might another packet not take that route? Redundancy, sure. So maybe, oh, we have 2 links. Let's just make sure we use both of them so that they're not, one of them is not being used too much. Can you think of maybe let's say I unplug a cable. I can't send a packet down that cable because now, yeah, exactly, routers might go down. If I unplug something, I can't send packets down that anymore because it's unplugged. So this layer needs to adapt to changes in the network, and thus we have to allow it to send packets down different routes. So it doesn't make any guarantees about the route that a packet takes, only the endpoints. All right, this is an example of the IP packet that we'll look at in more depth later, but the things to really notice here are that we have the source address that we talked about, we have the destination address, we also have a quick checksum over the header just so that if it somehow gets corrupted, we can detect that. It has a fragment offset, so if we fragment a packet into smaller packets, we need to be able to reassemble that correctly, so that's there for that. And of course, we have our data down at the bottom. So this is blue. You're not responsible for remembering the exact layout of a packet, but this is just some of the stuff that we talked about in its real byte form, or bit form, I guess, in this case. The IP protocol, again, is the IP protocol. IP stands for protocol. So IP protocol is Internet Protocol protocol. It's okay. The Internet Protocol, also known as IP, is the layer 3 protocol that pretty much all devices use with little to no exception, and no exception that I know of. The Internet Protocol uses IP addresses, so you've definitely heard of IP addresses before. These are addresses that identify a specific device on the internet. There are 2 versions of this. So IPv4 is 32 bits, which are usually written as 4 decimal octets separated by periods. So in this case, 35.163.72.93. You've probably seen something like this before. There is a newer version of this called IPv6. It's 128 bits, basically just because we were running out of IPv4 addresses. And we usually write it as 8 groups of 2 hex bytes. So if you've ever seen something that looks like hex, 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 colon, hex, 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 colon, that's IPv6. If you're missing some digits, that just means you should fill it with a bunch of zeros because there are a lot of 128-bit numbers. That's getting to the level of like cryptographic key. So they're not cryptographic keys, but they're the same size. So there are a lot of addresses for IPv6. The key with this is that because we are trying to address every device on the internet, we should make sure that every device on the internet has a unique address. Otherwise, there might be ambiguity as to where to send the packet to. Just think of them as being globally unique. We'll talk about how 2 devices might think they have the same IP address later, but don't worry too much about that for now. These addresses help nodes make decisions on where to forward the packet. So maybe one of my rules is, oh, if I receive a packet that starts with 1.5, I know I need to send it this way to get it close to its destination. Otherwise, I need to send it a different way. So these addresses are built to help routers route packets to where they're supposed to go. Another key thing about this layer, we're still talking about layer 3, the network layer, is reliability. So reliability basically ensures that packets are received correctly, or if there is some sort of error, then the packet isn't treated as being received. Again, this is implemented with the checksum that I mentioned in the IP packet frame earlier. But there is no cryptographic MAC. So, there's no key involved in the IP protocol. So this only protects against random errors. The adversary can still just tamper with your data and then compute the checksum, basically a hash themselves and forward the packet on. So it only protects against random errors. IP, it is not reliable. It is considered unreliable, and it provides something called best effort service. This means that you could accidentally lose a packet, you could accidentally receive a corrupted packet. If I send 2 packets, they might get to the destination in the wrong order. So these are all not really useful, or these are not great attributes that are part of the internet protocol, but it's going to be up to higher layers in order to build a reliable connection on top of this. So IP only says, okay, thank you for the packet. I'll do my best to get it to its destination, but there is absolutely no guarantee here whatsoever. All right, here's the diagram one more time. Layer 3 says, how do I get this packet from A all the way to D, routing it between these intermediate nodes? On top of this, we want to send data reliably. We don't always just want to send packets. Sometimes we want something that's more useful. So if something like SSH, it doesn't rely upon sending individual packets. It just wants to send some data and receive some data. And it wants to do it reliably because we don't want to just lose data out of nowhere. So the next layer is going to be how we build on top of this. Questions on layer 3 or internet protocol? All right. All right, so that brings us to layer 4, the transport layer. This provides the variable length data from any point to any other point. And it's going to rely on that packet sending structure that we talked about earlier. This layer also provides just useful abstractions in general that most applications are probably going to want at some point because IP just doesn't give us enough functionality on its own. The useful abstractions that we'll talk about are reliability. So we want to send something and make sure it's received by the other side. And we want to make sure that when we send it, say we send 2 pieces of data, those pieces of data are sent in the correct order. So I don't want my messages to accidentally be reversed into the wrong order. I also want something called ports. So when we're communicating with a computer, oftentimes that computer is doing multiple things at once. Maybe that computer has a web server, but it also has an SSH server. That computer only has one IP address. So ports are going to let us address multiple services, even on a single IP address. And we'll get more into that, how that works later on as well. The 2 main examples that we talk about are TCP and UDP, both of which will be covered, I think it's 2 lectures from now. All right, we talked about this already, so we'll skip it later because I realize I just wrote this slide twice. So, oh, this is a typo. This is definitely layer 4 transport layer. Give me one moment to fix this. All right. Anyway, layer 4 transport layer. This layer's job is just to make sure that when I transport arbitrary data, I will get it to the other side over any unreliable medium. So notice that layer 4 doesn't see this network of nodes anymore. It just knows that I can send packets from A to D, but it might be unreliable and it might be out of order. So it's the job of layer 4 to get this data to the other side intact. All right. That was pretty simple, mainly because most of the transport layer stuff is going to be talked about in really deep depth 2 lectures from now. But are there questions on layer 4? All right, we're actually almost to the end of this lecture, so we might end really soon. Finally, we have the application layer. This is probably the layer that you're most familiar with, even if you don't know it. So layer 7 provides applications and services to users. They are the things that we rely upon when we're using the internet. It relies upon this variable length data transport, basically sending data from anywhere to anywhere else, because most applications need to send data from one place to another. Any application that you've used that connects to the internet is a layer 7 application because it's an application. This could be something like web browsing. If you play video games, video games would be a layer 7 application. If you've ever texted someone on something that's not SMS on your phone, then that would also be layer 7. And something like Zoom, like I mentioned earlier, this is a layer 7 application because it relies upon sending my video data from me to the Zoom servers and then from the Zoom servers to all of you guys. All right, so now we're going to take all of this and put it together and see what it looks like for something to be sent from one point to another. When we're working with all of these headers, all of this had a bit of data that it had to send at the beginning and then the actual data underneath. As we go to lower layers, we're going to add additional wrappers around because the headers for something like layer 3 becomes just the data for layer 2, and then layer 2 adds its own headers, and then that all just becomes data for layer 1. Excuse me. Likewise, as we go to higher layers, we're going to peel off the headers because we don't need them anymore, and then we pass them to the upper layers. So when we send a message, we go from the top down, and then when someone receives a message, they need to go from the lowest back up to the highest layer. So let's walk through an example of an HTTP request just because it's something that we're sort of familiar with by now because of the web key. HTTP uses the TCP protocol. TCP is built on IP because everything runs on IP. And in this case, we're just going to say we're connected to the internet via Ethernet, and that Ethernet uses physical wires as its physical layer. So when my browser wants to send an HTTP request, it takes that get/HTTP/1.1. That's all just data, and it passes it to the TCP layer. TCP knows, okay, I have to send it to this certain port on the internet. So I'm going to say it's from port 1234. Just as an example, and I'm sending this to port 80 because web servers run on port 80. When TCP passes it to the IP layer, it's going to say, okay, I know that my own address is 1.2.3.4, and I need to send this to the web server, which is at 5.6.7.8. Notice that this is the final destination, but when we get to the layer below, that might not necessarily do with the final destination. So IP is like, okay, here's the data to the Ethernet layer. The Ethernet layer says, okay, I know my MAC address is this MAC address here, and the address of the router that I'm connected to is this address here. So I'm not trying to communicate with 5.6.7.8. I don't even know that I want to communicate with that address. I just need to know that this packet this frame gets sent to the router. So it's going to bundle all of that up, and that all gets turned into bits and transmitted over these wires. That's going to get sent to the router, and that's going to bounce around in the internet for a little bit, and eventually the wires at the server are going to receive the original or receive the new packet. Notice that from here, this is 20, this is 6D. This got turned into something else that's random, 89 and D5. Because these two servers are on different networks, they have completely different MAC addresses. That means that the MAC addresses changed when they were received from the wire. But notice that these IP addresses still stayed the same. So now the physical layer decoded this into the actual Ethernet frame. Ethernet goes, okay, I know that this frame was for me, so I will pass that up to the layer above me. IP goes, oh, I see, this message is to my IP address, so I will pass it up to the TCP layer. And then the TCP layer is going to see, oh, this is specifically for port 80. And I know that port 80 is currently being used for a web server. So finally, TCP is going, oh, I didn't include the last slide where this goes all the way back to the top. It's all right. TCP is going to pass this to HTTP, and HTTP sees, oh, this is a web request, or this is an HTTP request. I'm going to, get the data that I need, and then this whole process reverses itself for the HTTP response. This is analogous to what we talked about when we were talking about the mail. Each of these layers provides certain abstractions to the layers above, and the layers above rely on abstractions from the layers below. So wires provide just bits. Ethernet turns these bits into being able to send frames to anyone on your local network. IP turns this power into forwarding packets all across the internet, being able to deliver packets to anyone else on the internet. TCP makes this reliable, and it gives us other useful features. And the application HTTP gives us something that us as users can use. All right, questions on how this worked? How we communicated across the internet. All right, that is actually literally the end of this lecture. So as a summary, we talked about the internet, which is a global network of computers that can all communicate with each other. They have protocols which are agreed upon systems of communications in order to be able to speak with one another and actually understand what they're saying. The model that we're using is the OSI model, which layers together a bunch of protocols to eventually achieve what we call the internet. Layer 1 is the communication of bits. Layer 2 turns this into local frame delivery to anyone else on my network. These protocols, the protocol that we talked about was Ethernet, and that uses MAC addresses to address local devices. Layer 3 is global packet delivery. So now I can send packets to anyone else on the internet. The only protocol here is IP, which is used by pretty much anything that uses the internet. And these have IP addresses, which are 4 bytes or 16, sometimes 16 bytes, to address things and to know how to forward packets on to the next hop. Layer 4 turns this unreliable packet delivery into really just the useful transport of data. And again, we'll talk about this not next time, but I guess it would be next Monday when we talk about TCP and UDP. And finally, layer 7, now that we have this abstraction that just lets us send data from anywhere to anywhere else, layer 7 builds applications and services on top of this, such as the web or SSH or Zoom. And yeah, that is the end of this lecture. Like 35 minutes early. Perrin, do you want to do anything else other than this?
I would start tomorrow's a little early, but I literally don't think it's done. So
I see.
We may have lucked out. Is there anything from earlier that people want to see that we haven't shown?
Or does anyone have final questions, which I asked like 5 minutes ago? That's fine. Okay, if not, then everyone is free to go and enjoy the rest of their 35 minutes. Maybe that's a good thing because Project 2 design docs are due today. So yep, good luck on that, everyone, and I'll see you tomorrow.